May 16, 1943, Möhne Dam, Ruhr Valley, Germany. Oberingenieur Karl Simonis stood on the dam's observation platform, watching moonlight reflect off the reservoir's calm surface. As chief engineer responsible for the dam's maintenance, he'd inspected the structure that afternoon and found it perfect. 540 feet of concrete and stone, 130 feet thick at the base, holding back 140 million tons of water that powered the industrial heartland of Nazi Germany. His report to the district office concluded with absolute certainty. The Möhne Dam remains impregnable. No conventional explosive can penetrate the structure. Enemy aircraft cannot approach at low altitude due to anti-aircraft defenses. The reservoir is protected by torpedo nets. The dam is invulnerable to aerial attack. In 6 hours, those words would become a bitter epitaph. Bombs designed by a mad inventor named Wallis would skip across the water like stones, sink against the dam face, and explode at precise depth, triggering pressure waves that would tear 250 feet of concrete structure apart and release a wall of water that would devastate the Ruhr Valley below. The German confidence. The German High Command had laughed in 1941 when intelligence reports described British research into bouncing bombs designed to destroy dams. The report seemed absurd on every level. Bombs didn't bounce. This violated basic physics. They couldn't be delivered with the precision required to hit dam faces. And even if they could somehow be placed correctly, they lacked sufficient explosive power to damage massive concrete structures. Dams were invulnerable to aerial attack. This was established engineering fact, confirmed by German military engineers who'd analyzed every conceivable defensive scenario. The Allies lacked the technical sophistication to develop weapons that could threaten German dams. British engineers, while competent, were bound by conventional thinking that couldn't produce revolutionary weapons. The bouncing bomb concept was obvious desperation, fantasy physics invented by scientists who didn't understand practical engineering. Wallis, the British engineer developing the weapon, had been called a mad inventor by his own colleagues. He was a brilliant but impractical dreamer who pursued impossible ideas while wasting resources needed for conventional weapons. His bouncing bomb had been rejected by the Ministry of Aircraft Production, dismissed by senior RAF officers, and ridiculed by engineers who understood that bombs simply didn't work the way Wallis proposed. By May 17, 1943, Wallis's impossible weapon had destroyed 2 major dams, damaged a third, and released over 330 million tons of water that devastated Germany's industrial heartland. The attack demonstrated that conventional wisdom about engineering limitations could be catastrophically wrong. That one brilliant mind pursuing an impossible idea could create weapons that changed warfare, and that German confidence in their dams' invulnerability had been built on assumptions that didn't account for British ingenuity. The mad inventor Barnes Neville Wallis was 54 years old in 1940 when he first conceived the idea of destroying German dams through aerial attack. He was already famous in British aviation circles. The brilliant engineer who designed the R-100 airship, developed geodetic construction for the Wellington bomber that made it extraordinarily damage-resistant, and created numerous innovations in aircraft structures. But he was also known for pursuing ideas his colleagues considered impractical or impossible. He'd spent years advocating for earthquake bombs, enormous weapons weighing 10 tons or more, dropped from extreme altitude to penetrate deep underground before exploding. The Air Ministry had rejected the concept as impractical. No existing aircraft could carry such weapons. Developing them would require resources better spent on conventional bombs, and the tactical benefits were speculative. Wallis was undeterred by rejection. He'd spent decades in engineering proving that impossible solutions often worked better than conventional approaches. His geodetic construction method for aircraft had been dismissed as too complex, too expensive, too different from traditional methods. But Wellington bombers built using geodetic structures survived damage that would destroy conventionally built aircraft. Bullets and shell fragments would pass through the lattice structure without causing catastrophic failure. When Wallis proposed destroying German dams in 1940, his colleagues' initial response was dismissive. Dams couldn't be destroyed by bombs. The structures were too massive, too well protected by geography and defenses. Even if bombs could reach the dams, they lacked sufficient explosive power to damage thick concrete structures. Wallis approached the problem methodically, applying engineering analysis rather than accepting conventional wisdom. He studied German dam construction, analyzing structural properties of the Möhne, Eder and Sorpe dams that supplied water and hydroelectric power to the Ruhr industrial region. He examined photographs, consulted German engineering publications, and built scale models to test his theories. His analysis revealed that dams were vulnerable despite their massive construction. The structures were designed to resist steady water pressure, not sudden shock waves. If an explosive could be detonated against the dam face underwater, creating a pressure wave that would hammer the structure, the shock could crack the concrete and potentially cause catastrophic failure. The challenge was delivery. Dropping bombs from high altitude was useless. The bombs would miss the narrow dam faces, and even direct hits wouldn't penetrate to optimal depth before exploding. Low-altitude bombing was suicidal. German anti-aircraft defenses would destroy attacking aircraft, and torpedo nets protecting the reservoirs would intercept any conventional torpedo attack. Wallis needed a weapon that could be delivered from low altitude, bypass torpedo nets, strike the dam face precisely, sink to optimal depth, and detonate to create maximum pressure wave effect. No such weapon existed. He would have to invent it. The bouncing bomb, an impossible solution. The solution came to Wallis while skipping stones across a pond with his children in 1941. He watched stones skip across water, maintaining forward momentum through multiple bounces, and realized the same principle could be applied to bombs. A cylindrical bomb spinning backward at high speed could bounce across water like a stone, skip over torpedo nets, strike the dam face while still possessing significant kinetic energy, then sink against the structure. The physics were complex but achievable. The bomb would need backspin, approximately 500 RPM, to create lift as it contacted water, causing it to bounce rather than dive. The aircraft would release the bomb from precisely 60 feet altitude at exactly 240 mm/h airspeed. The bomb would bounce across the water surface, losing energy with each bounce, but maintaining forward momentum toward the target. Upon striking the dam face, the bomb's backspin would cause it to roll down the sloped concrete surface while maintaining contact with the dam. It would sink to approximately 30 feet depth, the optimal position for creating a pressure wave that would damage the structure. A hydrostatic fuse would detonate the bomb at that depth, creating a shock wave that would hammer the dam face from underwater. Wallis calculated that a bomb containing approximately 6,600 pounds of Torpex explosive, detonated at 30 feet depth against the dam face, would create a pressure wave of roughly 10,000 pounds per square inch, sufficient to crack even massive concrete structures. When he presented his concept to the Air Ministry in 1941, the response was immediate rejection. The physics seemed preposterous. Bombs didn't bounce. They would shatter on water impact or dive beneath the surface. Even if a bomb could bounce, controlling its trajectory with the precision required was impossible. The entire concept was fantasy. Other objections followed. Releasing a spinning bomb from 60 feet altitude at night required impossible precision. Pilots couldn't maintain such exact altitude and speed During combat operations, the bomb would probably break apart from spin forces or water impact. Even if the weapon worked in theory, manufacturing was impractical. The specialized bombs would require production capacity better used for conventional weapons. Wallis was rejected, dismissed, and told to stop wasting time on impractical fantasies. He persisted anyway, using his own time and resources to develop the concept further. Proving the impossible, Wallis built scale models and tested them in water tanks at the Road Research Laboratory in Harmondsworth. He experimented with different shapes, spheres, cylinders, ellipsoids, testing which geometry provided optimal bouncing characteristics. He varied spin rates, release heights, and forward velocities, documenting how each variable affected bounce distance and behavior. The early tests failed repeatedly. Spherical bombs tended to bounce erratically, veering off course unpredictably. Release height proved critical. Too high and the bomb would shatter on water impact. Too low and it wouldn't bounce properly. Spin rate had to be precise. Too slow and the bomb wouldn't bounce. Too fast and centrifugal forces would tear it apart. Wallis refined his calculations after each failure, adjusting parameters incrementally. He discovered that cylindrical bombs provided more consistent bouncing than spheres. He determined that 500 RPM was optimal for the backspin, enough to create lift on water contact, but not so much that structural integrity was compromised. He calculated that 60 feet was the ideal release altitude, low enough that the bomb wouldn't shatter, but high enough to allow proper trajectory development. By early 1942, the scale models were working consistently. Small cylindrical bombs with backspin would bounce across water tanks, strike barriers representing dam faces, roll down the surfaces, and come to rest at predictable depths. Wallis filmed the tests using high-speed cameras, documenting every detail of the bomb's behavior. The footage was remarkable, visual proof that the impossible was possible. Wallis prepared a new presentation, armed with film evidence, mathematical calculations, and scale test results. He approached the Ministry of Aircraft Production again, this time with data that couldn't be dismissed. In February 1943, nearly 2 years after his initial proposal, Wallis finally secured support from Air Chief Marshal Charles Portal, Chief of the Air Staff. Portal understood that innovative weapons sometimes came from unconventional thinking. He authorized development of the weapon, now designated upkeep, and formation of a specialized squadron to deliver it. Building the weapon, the bomb Wallis designed, was enormous. A cylinder 60 inches in diameter, 50 inches long, weighing 9,250 pounds, including 6,600 pounds of Torpex explosive. The outer casing was constructed from welded steel plate 3/8 of an inch thick, strong enough to withstand water impact and spin forces, but light enough that the weapon could be carried by modified Lancaster bombers. The bomb had to be spun to 500 RPM before release, using a hydraulic motor powered by the aircraft's engines. The spin mechanism was complex, a belt drive system connected to one of the Lancaster's auxiliary power units, requiring careful engineering to ensure the spinning bomb didn't create dangerous vibrations that would affect aircraft handling. Each bomb had to be perfectly balanced. Any eccentricity in weight distribution would cause violent vibrations when spun to 500 RPM. Workers used precision machining to ensure tolerances measured in thousandths of an inch. Filling the bombs with 6,600 pounds of Torpex explosive was delicate work. The explosive was cast into the cylindrical casings under carefully controlled temperature conditions. Air pockets had to be eliminated. Any voids in the explosive would create weak points that could cause premature detonation or reduced effectiveness. Only 19 upkeep bombs were built for the actual operation, each one handcrafted, each one representing months of engineering development and manufacturing effort. The weapons cost approximately $7,000 each, roughly $400,000 in modern currency, making them among the most expensive bombs ever developed. Forming 617 Squadron simultaneously with bomb development, the RAF formed 617 Squadron specifically to deliver the weapons. The squadron was activated on March 21, 1943, at RAF Scampton in Lincolnshire. Wing Commander Guy Gibson, a 24-year-old combat veteran with 173 bombing operations, was appointed to command. Gibson had earned the Distinguished Service Order and Bar, the Distinguished Flying Cross and Bar, decorations awarded for exceptional combat leadership and bravery. He'd completed tours on both bombers and night fighters, accumulating more operational experience than most officers twice his age. He was tough, demanding, and absolutely committed to operational success, regardless of cost. Gibson was told only that he would command a new squadron for a special operation requiring low-level precision flying. The target wasn't revealed initially. Operational security demanded that only essential personnel know the mission's purpose. Gibson's task was to select crews, train them to standards required for the mission, and prepare them for combat without explaining what they would attack. He selected crews from across Bomber Command, men with proven skill and courage, pilots known for precision flying, navigators capable of pinpoint navigation, bombardiers with exceptional accuracy records, gunners with combat experience. The selection process was ruthless. Gibson wanted the best, and mediocrity wasn't tolerated. The crews he assembled represented Bomber Command's elite. Many had already completed operational tours, 30 missions over Germany, the standard before rotation to training duties. They'd volunteered to return to combat, knowing that second tours had significantly higher casualty rates than first tours. They didn't know what mission they were training for, but they understood it would be dangerous and important. The training began in late March 1943 and continued intensively through mid-May. The crews practiced low-altitude night flying, learning to maintain precisely 60 feet altitude, so low that aircraft sometimes struck water with their propellers, bending the blades and requiring replacement. Several aircraft returned with propeller damage after pilots misjudged altitude by mere feet. The altitude requirement created a particular challenge. 60 feet was too low for conventional altimeters to measure accurately. Standard aircraft altimeters used barometric pressure to calculate altitude, accurate at higher altitudes but unreliable near ground level where local pressure variations created significant errors. Wallis developed an ingenious solution: 2 spotlights mounted under the aircraft, angled so their beams converged at exactly 60 feet altitude. When the light pools merged into a figure 8 pattern on the water, the pilot knew he was at correct altitude. The system was simple, reliable, and didn't require electrical instruments that could fail. For distance measurement, knowing when to release the bomb, Wallis created a simple but effective sight: a wooden triangle with 2 nails positioned at specific points, corresponding to the width of the dam towers as seen from optimal release distance. The bombardier would look through the sight. When the towers exactly filled the space between the nails, the aircraft was at correct release range, approximately 450 yards from the dam. Flight Lieutenant Bob Hutchison, navigator on Shannon's crew, later described the training. "We flew at 150 feet or lower, sometimes 60 feet, at 240 meniatas over British countryside at night. We navigated by visual landmarks visible in moonlight. The margin for error was 0. If we were 30 seconds late arriving at the target, the attack timing would be wrong. If we navigated to the wrong position, we'd miss the dam entirely. If we misjudged altitude by 20 feet, the bomb wouldn't bounce correctly." We practiced for 6 weeks, flying training missions almost every night. By mid-May, we could execute the attack in our sleep. Security was absolute. The crews knew they were training for a special operation, but weren't told the target until May 15th. Just days before the mission, they weren't allowed to discuss training with anyone outside the squadron. The secrecy created frustration, but operational security demanded that target information be restricted until the last possible moment. The briefing on May 15th, Gibson finally revealed the targets to his crews. The entire squadron assembled in the briefing room at RAF Scampton as Gibson stood before a large map of Germany and explained, "Gentlemen, you will attack 3 dams in the Ruhr Valley, the Möhne, Eder and Sorpe dams. These dams provide water and hydroelectric power to German industry. The weapons you will carry were designed specifically for this mission by Wallis. They are spinning cylindrical bombs that will bounce across water, strike the dam faces, sink to optimal depth, and explode underwater." He continued, "This is the most important bombing mission of the war. It is also among the most dangerous. You will fly at 60 feet altitude across Germany at night, attack heavily defended targets, and return across 400 miles of hostile territory. Some aircraft will not return. Some crews will not survive. But if we succeed, we will strike a blow against German industry that will resonate throughout the war." The revelation produced mixed reactions. Some crews were relieved to finally understand what they'd been training for. Others were apprehensive about attacking targets deep in Germany at extremely low altitude. But all were determined to succeed. The German defences. While Wallis and 617 Squadron prepared, German engineers remained confident their dams were invulnerable. The Möhne Dam's defences included 24 light anti-aircraft guns positioned on the dam itself and surrounding hills, providing overlapping fields of fire across approach routes. Torpedo nets, heavy steel cables suspended from floats extending 35 feet below the water surface, protected the reservoir. The Eder Dam had no anti-aircraft defences at all. German planners considered the geography sufficient protection. The dam sat at the end of a narrow valley surrounded by 1,000-foot hills. Aircraft approaching would need to fly over the hills, dive sharply into the valley, level off at extremely low altitude, release weapons, then pull up sharply to avoid hitting the hills beyond. The maneuver was considered aeronautically impossible, especially at night. German military engineers had analyzed the theoretical threat of aerial attack against dams and concluded the risks were minimal. A staff paper from January 1943 stated, "The strategic dams of the Ruhr are effectively invulnerable to aerial attack. Resources devoted to dam defense should be minimal." The assessment was reasonable and logical, based on understanding of conventional weapons and tactics. It didn't account for Wallis's unconventional approach, or the RAF's willingness to train crews to execute tactics that seemed impossible. Operation Chastise, the attack Gibson's 617 Squadron, departed RAF Scampton at 2128 hours May 16, 1943. 19 Lancaster bombers, each carrying a single upkeep bomb spinning at 500 RPM, headed toward Germany. The aircraft flew in 3 waves, following different routes designed to avoid major flak concentrations. The route covered approximately 400 miles each way across occupied Europe. The bombers flew at wave-top height, 60 to 150 feet, to avoid German radar detection. The low-altitude flight was beautiful and terrifying. Crews watched German countryside pass beneath them at 240 mph, flying so low that startled farmers looked up at British bombers passing overhead. Disaster struck en route. At 2313 hours, Flight Lieutenant Bill Astell's aircraft struck high-tension power lines near Marbeck. The Lancaster crashed and exploded, killing Astell and his entire crew instantly, the first loss before even reaching the target. At 0028 hours May 17th, Gibson's aircraft reached the Möhne Dam. He orbited the reservoir once, surveying the target. The defensive guns opened fire immediately, tracers arcing toward the Lancaster, shells exploding around the aircraft. Gibson began his attack run, descending to 60 feet altitude, with spotlights creating the figure 8 pattern on the water that indicated correct height. German gunners tracked the aircraft, firing continuously. Gibson held steady despite the fire. At 0028 hours and 40 seconds, his bombardier called "Bomb Gone." The spinning cylinder dropped away, struck the water, bounced, once, twice, 3 times, each bounce carrying it closer to the dam face, exactly as Wallis had calculated. The bomb struck the dam's curved face, rolled down the sloped concrete while maintaining contact with the structure, and sank to optimal depth. 30 seconds later, the weapon detonated. A massive water column erupted from the reservoir, spray and foam climbing 1,000 feet into the air. Gibson circled, watching for damage. The dam had been cracked, but not catastrophically failed. The attack would need to continue. The second aircraft, piloted by Gibson's closest friend, Flight Lieutenant John Hopgood, began its attack run at 0030 hours. Hopgood's Lancaster had been hit by flak earlier and was burning. German gunners concentrated devastating fire on the approaching aircraft. Hopgood continued the attack despite his aircraft disintegrating around him, but the burning Lancaster was too high. The bomb bounced over the dam and exploded in the power station beyond, missing the dam face entirely. Hopgood attempted to climb away, but the fuel tanks exploded at approximately 500 feet. The aircraft broke apart in mid-air. 2 crew members escaped. 5 others, including Hopgood, died in the fireball. The attacks continued. Flight Lieutenant Harold Martin attacked third at 0034 hours, his bomb striking the dam face precisely. Squadron leader Henry Young attacked fourth at 0038 hours, his bomb adding more visible cracking. Water began seeping through the damaged section. At 0049 hours, Flight Lieutenant David Maltby attacked fifth. His bomb struck in nearly the same location as Young's bomb. The explosion at 0050 hours was the final blow. The accumulated damage from 5 bombs had exceeded the concrete structural capacity. The dam failed catastrophically. A 250-foot section collapsed, releasing 140 million tons of water in a wave that devastated the valley below. Gibson circled overhead, watching the breach widen, radioing the code word that signaled the Möhne Dam had been destroyed. The flood Ober-Ingenieur Simonis watched in horror as the dam he declared invulnerable collapsed into the reservoir. Water exploded through the breach, a wave 25 feet high roaring down the valley, destroying everything in its path. The sound was indescribable, like continuous thunder, drowning out even aircraft engines overhead. The flood wave traveled down the Ruhr Valley at approximately 15 miles per hour. The town of Himmelpforten was destroyed within minutes. Niederenz was inundated at 0107 hours, the flood arriving without warning in darkness. At Neheim, the wave destroyed a railway bridge. Wicked was flooded at 0120 hours. Factories submerged, equipment destroyed, power generation halted. German casualty estimates recorded approximately 1,294 deaths from the Möhne Dam flooding, mostly civilians. Many victims were foreign workers, forced laborers from Poland, Soviet Union, France, and other occupied countries brought to work in war industries. The true death toll was probably higher. Many bodies were never recovered. The Eder Dam, while the Möhne battle raged, other aircraft proceeded to the Eder Dam. At 0139 hours, Flight Lieutenant David Shannon began his attack run. The approach was extraordinarily difficult, flying over 1,000-foot hills, diving into a narrow valley, leveling off at 60 feet, while accelerating to attack speed. Shannon aborted his first approach, then his second, third, fourth, and fifth. On his sixth attempt, he finally achieved correct geometry and released his bomb at 01:47 hours. The weapon struck the dam face off center. The explosion damaged the structure but didn't cause failure. Squadron leader Henry Maudslay attacked next at 01:49 hours. His bomb was released slightly late, striking the dam parapet rather than the face below. It exploded directly beneath Maudslay's aircraft, severely damaging the Lancaster. Maudslay attempted to fly the damaged bomber back to England, but was shot down near the Dutch coast. He and his entire crew were killed. Flight Lieutenant Les Knight attacked at 01:52 hours. His approach was perfect. The bomb struck the dam face center, sank to optimal depth, and detonated. At 01:54 hours, the Eder Dam failed. A 200-foot section collapsed, releasing 202 million tons of water. The flood destroyed multiple towns and disrupted transportation infrastructure across a wide area. The return. The surviving aircraft turned for home, flying at low altitude across 400 miles of hostile territory. German defenses were fully alert, night fighters were scrambling, anti-aircraft batteries were firing at any aircraft detected. Squadron leader Henry Young was shot down at 01:58 hours by German night fighters. Flight Lieutenant Warner Otley was shot down at 02:35 hours by anti-aircraft fire. Pilot Officer Vernon Byers was shot down at 02:50 hours. The surviving aircraft struggled home individually, each crew knowing German defenses were hunting them. Gibson's aircraft landed at RAF Scampton at 04:15 hours. Other surviving aircraft landed over the next hour. Ground crews counted. 11 of 19 aircraft had returned. 8 aircraft and 53 crew members were missing, all dead or captured. The Aftermath 6117 Squadron lost 41% of its aircraft and crew, an extraordinarily high loss rate. But the operation achieved its objectives: 2 major dams destroyed, 1 damaged, massive flooding across the Ruhr Valley, industrial disruption lasting months. German casualties from both floods totaled approximately 1,600 deaths, though the true number was probably higher. The industrial impact was significant. Hydroelectric power generation disrupted for months, water supplies reduced, coal mines flooded, transportation infrastructure damaged. But Germany demonstrated remarkable resilience. The dams were partially repaired within 6 months. Industrial production declined temporarily, but recovered as alternatives were brought online. The strategic impact was real but limited. The raids didn't cripple German war production. However, the psychological and propaganda impact was enormous. The raids demonstrated British technical ingenuity and RAF operational capability. They proved that structures German engineers declared invulnerable could be destroyed by creative thinking and precise execution. German respect for British technical capabilities increased significantly. Intelligence officers could no longer dismiss reports of Allied weapons as impossible. He mad inventor vindicated Barnes Wallis, the mad inventor whose ideas had been dismissed as impractical fantasies, was suddenly a national hero. The press celebrated his genius in articles with headlines like "The Man Who Broke the Dams" and "Britain's Secret Weapon Genius." The Air Ministry publicly praised his contributions, the same organization that had rejected his proposals for 2 years. King George VI summoned him to Buckingham Palace for a personal audience and thanked him for his service to the nation. Engineers who'd mocked his bouncing bomb concept now studied his designs with admiration, hoping to replicate his success in their own projects. The Institution of Civil Engineers invited him to deliver lectures on dam destruction and explosive effects. Universities offered honorary degrees in recognition of his engineering achievements. But Wallis was characteristically modest about the achievement. In a letter to a colleague, written June 1943, he reflected, "The dam raid succeeded because we refused to accept that conventional limitations were absolute. Engineers told me bombs couldn't bounce. I proved they could through testing and calculation. Tacticians told me precision delivery was impossible. 617 Squadron proved otherwise through skill and courage. Strategists told me dams were invulnerable. The Möhne and Edda proved differently through proper weapon design and placement. The lesson is not that I am particularly clever, but that we must question assumptions about what is possible. Most innovations fail, not because they're technically impossible, but because we convince ourselves they cannot succeed before we attempt them. The bouncing bomb worked because we tried rather than accepting it was impossible. I regret the loss of life, both the RAF crews who died delivering the weapons and the civilians who died in the floods. War is tragedy, regardless of which side claims victory. The 53 men of 617 Squadron who didn't return deserve the credit for the operation's success. They flew the mission knowing full well the dangers, executed with precision under fire, and died ensuring others could succeed. But I am proud that British engineering rose to a seemingly impossible challenge and achieved what others thought could not be done. The dams stood as symbols of German industrial might and defensive invulnerability. We destroyed them not through brute force, but through creative thinking applied to difficult problems. That is what engineering should be, finding solutions to challenges others consider unsolvable. Wallis continued developing innovative weapons throughout the war. His tall boy earthquake bomb, a 12,000-pound streamlined weapon dropped from 20,000 feet, could penetrate deep underground before exploding, destroying hardened targets including submarine pens, V-weapon sites, and railway tunnels. Tallboy bombs sank the German battleship Tirpitz in November 1944 after conventional bombs had failed for years. His Grand Slam bomb, 22,000 pounds, the largest conventional bomb of World War II, could penetrate 20 feet of concrete or 100 feet of earth before detonating. Grand Slam bombs destroyed viaducts, collapsed tunnels, and demolished underground facilities that were invulnerable to other weapons. Post-war, Wallis contributed to supersonic aircraft development, designed variable geometry swing wings that influenced modern fighter design, and continued pursuing innovative concepts that others considered impractical. He worked at his drawing board into his late 80s, still sketching ideas, still calculating, still believing that impossible was just another engineering challenge. He was knighted in 1968 for his contributions to British engineering and defence. Sir Barnes Neville Wallis died October 30, 1979, at age 92, still working on advanced concepts at his home drawing board. His obituary in the Times called him the greatest British engineer of the 20th century. The final accounting operation. Chastise demonstrated several enduring truths about innovation and warfare. Revolutionary weapons often come from individuals willing to question conventional wisdom and persist despite rejection. That impossible usually means nobody has succeeded yet, rather than cannot be done. That defensive planning based on assumptions about enemy capabilities is catastrophically vulnerable when the enemy thinks creatively, and that engineering genius combined with operational excellence can overcome overwhelming defensive advantages. German engineers had analyzed their dams using sound engineering principles and concluded they were invulnerable to aerial attack. Their analysis was correct given conventional weapons and tactics available in 1941. They failed to imagine that someone would develop an unconventional weapon specifically designed to exploit weaknesses in structures designed for different loading conditions. The bouncing bomb represented a new weapon category, one that succeeded not through overwhelming force, but through precision, timing, and physics that defenders hadn't considered. The weapon worked because Wallis understood both the target's vulnerabilities and the delivery system's capabilities, then designed a weapon that matched both requirements perfectly. 6M17 Squadron's achievement was equally remarkable, executing tactics that seemed aeronautically impossible, delivering weapons with precision measured in feet against defended targets, flying at altitudes where the slightest error meant death. The squadron suffered 42% losses but accomplished its mission, proving that exceptional crews could succeed at missions that seemed suicidal. The legacy of Operation Chastise extended far beyond the immediate military impact. The raid demonstrated that British engineering and RAF operational capability could achieve objectives previously considered impossible. It proved that Germany's defensive systems, despite their sophistication, were not invulnerable. It provided a template for precision special operations that influenced post-war military planning. Most importantly, it validated Barnes-Wallis, the mad inventor whose ideas had been dismissed, whose proposals had been rejected, whose concepts had been ridiculed by colleagues who knew that bombs couldn't bounce and dams couldn't be destroyed. He'd proven that persistence, innovation, and willingness to challenge conventional wisdom could overcome institutional resistance and create weapons that changed warfare. Epilogue: Oberingenieur Karl Simonis survived the war and worked on dam reconstruction during Germany's post-war recovery. He supervised rebuilding of the Möhne Dam, completed in 1949 using more modern construction techniques and stronger materials. The new dam incorporated lessons learned from the destruction, different structural design, improved resistance to shock loading, defensive considerations that Simonis's 1943 design had lacked. In a 1967 interview for a German engineering journal, Simonis reflected on the night of May 16, 1943. I watched bombs bounce across water like stones. Something I'd been taught was impossible. I watched them strike our dam with precision that should have been unachievable from aircraft at night. I watched explosions at depths calculated to maximize structural damage through underwater shock waves. I watched 250 feet of concrete that I'd declared invulnerable collapse into the reservoir. We had convinced ourselves the dams were safe because we couldn't imagine how they could be attacked. We understood conventional bombs dropped from conventional altitudes using conventional tactics. We prepared defenses against those conventional threats. We didn't imagine that a British engineer would spend 2 years developing an entirely new type of weapon specifically designed to exploit vulnerabilities in structures designed for static loading rather than dynamic shock. We didn't imagine that RAF crews would train to fly at 60 feet altitude at night, maintaining that altitude within feet while navigating through defended airspace. We didn't imagine that attackers would be willing to accept 40% losses to accomplish their mission. Barnes-Wallis thought differently than we did. He didn't accept that our dams were invulnerable. He studied them until he understood how they could be vulnerable. He didn't accept that bombs couldn't bounce. He tested until he proved they could. He didn't accept that precision delivery was impossible. He developed methods to achieve it. He didn't accept that one weapon couldn't destroy a massive concrete structure. He calculated the physics until he understood exactly how much explosive at exactly what depth would cause catastrophic failure. We called him a mad inventor because his ideas violated our understanding of what was possible. He was mad like a genius, visionary enough to see solutions others missed, persistent enough to develop them despite rejection, brilliant enough to succeed where conventional thinking said he must fail. His madness destroyed our dams, our sanity, our belief that we understood all possible threats, failed to protect them. The lesson I learned that night The lesson that shaped my entire post-war career was that defensive engineering must account not just for known threats, but for threats we haven't imagined yet. The enemy will think of things we don't expect. The difference between invulnerable and destroyed is often one brilliant mind pursuing an idea everyone else dismisses as impossible. Wallis was that brilliant mind. We called him mad. History called him genius. Both were correct. Genius and madness are often separated by whether the impossible idea actually works. His did. Our dams didn't survive. That's the only measure that matters. They called him the mad inventor. Wallis, the eccentric engineer who proposed bouncing bombs across water, who insisted precision delivery was achievable, who claimed that massive concrete dams could be destroyed by aerial attack, whose ideas were rejected by the Ministry of Aircraft Production, dismissed by senior RAF officers, and ridiculed by engineers who knew that bombs simply didn't work the way he proposed. Until his bomb bounced across the Möhne reservoir exactly as he'd calculated, struck the dam face with impossible precision, sank to optimal depth and exploded, creating shockwaves that tore 250 feet of invulnerable concrete apart and released 140 million tons of water that devastated the Ruhr Valley and proved that mad inventors who refuse to accept impossibility sometimes change the world. The mad inventor had sliced a dam in half. The impossible weapon had worked perfectly. The fantasy had become devastating reality. And by the time German engineers understood what had happened, 2 dams were destroyed, their valleys were flooded, 1,600 people were dead. And Wallis had proven that the impossible just requires more effort than the possible, and that one brilliant mind armed with physics, persistence, and a willingness to fail repeatedly until success is achieved can defeat defenses that armies consider impregnable.